Morning, buenos dias, egunon, buondì. It's a pleasure for me to introduce from University of Aquila, Maria Pia Palombaro. She talks about differential inclusion politics.
So thank you very much for the invitation, and thank you, Eugenio and Luca, for organizing this very nice event. And I would like to thank Luca in particular for the amazing hospitality. Thank you so much. I'm very happy to be here. So I've known Enzo since 24 years, it seems, right? Do you agree?
You're younger than 24. This is not possible.
So I was his PhD student, and I think I was the first PhD student and the last, because after me, he decided not to repeat the same mistake. And so during my PhD, during those years we were in Rome, I thought that Enzo was a very that he had no interest other than mathematics. He always looked so focused on problems. He always looked very, very serious. So we had this interaction, which was based on mathematical discussions only. And I can remember just one event, which was out of equilibrium, let's say so, which was when I was writing my first paper with Marcello Consigliano, as you may know. So one day I was in the computer's room, the common room, and I was taking the file. And then at some point I left my position with the account open to go and get a coffee. And while I was away, there was a friend of mine, Francesco De Vita, who was around. And he decided to make a joke to me. And so he inserted in the text file an acknowledgement to himself. So when I went back to the computer, I printed the file without noticing this acknowledgement. And then I took the draft and I went to Enzo in the Falegnameria. Falegnameria was a building where he had his office with other people. So we sat at the entrance of the Falegnameria and started checking this draft. I had not realized anything. And when he arrived at the last page where this acknowledgement was, he started shouting, saying, "No, it's not possible. Look what they do." So the acknowledgement read, "We thank our best friend, Francesco De Vita, for his valuable comments on the realization of gigantic characters. Okay. And then he took my draft and he went around all the offices in Falegnameria, showing this to all the people there. Look what they do. There is no hope. There is no hope. So I was very embarrassed, and then I took the draft and I went back to the computer room. So
Did you feel Francesco? Did you feel Francesco?
No, Francesco was so happy.
So Maria Pia, may I ask you just in 5 seconds, I will record you to the, I wish to sincerely thank Francesco Petita, and I sent him the mail.
Yes, so I wish to thank Francesco Veletta for the amazing job that he made 20, 25, 26 years ago. Thank you very much. Okay, so then I finished my PhD, and when I finished, Enzo's recommendation was, okay, now you go, you travel, and you visit as many places as possible. These were prophetic words, in fact. I hold the record of the number of postdocs done in my life. I know no other person who did that many postdocs as I did. But it was a very good part of my life. And then for many years after my PhD, we didn't talk and meet too much, too often, but I know he was busy fighting his battles that you know better than me. And then a few years ago, 2 or 3 years ago, maybe, he proposed to work together on the problem that I'm with. And so we started talking again. First, we were meeting online, essentially online meetings every 3 weeks and then every 2 weeks. And in the past year, we were meeting on a weekly basis every week. And so we started talking about many things, many issues, and I discovered that Enzo has lots of interest. It's not that serious as I thought, as I remember. And to my great surprise, I found out that we have common interests. And in particular, we are both very fond of politics, of foreign politics. So in our meetings, while chatting, at some point, we always switch to politics. And I enjoy this very much because we have exactly the same views. So I was very happy about that. Not only that, we also share some musical preferences. For example, we both like Mercedes Soda. And last April, on the day of liberation, 25th of April, I wanted to post a song of hers on my status. And then I checked WhatsApp and I discovered that he had posted the very same song that I wanted to post. Because he woke up actually with me. And so then I didn't do that because he didn't want him to think that I was posting. Yeah, so I'm very happy that we had the opportunity to get closer together and know each other better, not only mathematically. And now, on a more serious note, I must say that I enjoy these meetings, especially in the past year, since with all the things that are happening around the world, talking with that, so it was a relief for me because I could express all my concerns and I knew that he could understand. And I would like to take this opportunity to express my deep admiration for the stance that Enzo publicly took as an academic in regard to the fundamentality of our time. So it took courage, and he had this courage, and he is the only person among all the people I know that did it. So I have a deep respect because of this. And now that he retires, I'm sure that he will not be resting on a beach all the time. I'm sure that he will devote his time and energies to interesting projects that I'm sure I will support. So I wish you all the best for this new chapter of your life. Thank you. Okay, now let's switch to mathematics. I will talk about this problem. This problem starts with PhD thesis on it. So now we are closing a loop. And this is also a collaboration with Nathan Albin from Kansas. Okay, I need this.
No, the slimmer one.
This later. Okay, so the problem that we studied is a differential inclusion that originates in the problem of bounding the effective conductivity of a composite material. This is something that Enzo studied for a long time in his life, and he began his career with this kind of problems. So now I will first formulate the differential inclusion, and then I will digress a bit to explain the physical motivation of the problem. No?
La freccia in giù.
La freccia in giù, che non è molto intuitivo. So this is the differential inclusion. We are given a diagonal matrix S with eigenvalues S1, S2, S3 that are strictly positive and not the same. They are all distinct, okay? And their sum is 1. K of S is the set of all symmetric matrices, 3 by 3 matrices, that can be written as a multiple lambda is any scalar, positive or negative, of a conjugate of the matrix S, where R is the rotation, an element in SO3. Okay, so K of S is the set of all such matrices. This is a subset of symmetric matrices. So the eigenvalues of these matrices have constant ratio. And the differential inclusion is the following. We look for maps, U, Sobolev maps, whose gradient lies in this set. It takes values in the set K almost everywhere. And these maps, U, belong to this space. So U consists of a periodic part plus an affine part. Okay. I will give more details about this, and I will explain better which kind of solutions we want to find. We would like to characterize all these affine boundary conditions that can be realized by maps that takes values in this set, even not exactly this set, but close to this set. This is the general problem. And now let me, like this, yes, give you the physical motivation, the physical motivation for this paper, which is to be found in the polycrystal problem. So a composite material is a material consisting of different materials, different conducting materials, and the conductivity of a composite material is described by a field sigma, which is matrix values, which takes values in the set and d by d now. In general, the dimension, symmetric matrices, and that satisfies this ellipticity condition, almost everywhere. Okay. The effective conductivity sigma star is associated to sigma, is a constant matrix that describes the overall behavior of our composite material. So the pointwise conductivity is described, is determined by sigma, but this material behaves overall like a homogeneous material with constant conductivity sigma star. This is the meaning of this matrix, and its definition is the following. So sigma star is defined by this variational problem, is the infimum of this quadratic form. So sigma star applied to Xc is the infimum over all Sobolev functions with this boundary condition Xc, which is here. Okay, and this can be written also in a vectorial form by taking coupling pairs of linearly independent vectors Xc. So sigma star is constant, does not depend on Xc. We can write this also in this way. So the trace of A sigma star A transpose, where A now is a d by d matrix, is given by this variational problem. Okay, it's the same. It's the same formulation. And those who are familiar with this formula will recognize that sigma star is the H limit of the periodic rescaling of sigma. So if we define sigma epsilon as sigma over or x over epsilon with periodicity the unit cube, well, I haven't said that, then H convergence means this, that for each f in H minus 1, for every fixed right-hand side, the solution U epsilon of this elliptic equation will converge within each one to the solution of this limit problem, where here we have sigma star. Okay, and we have convergence also of sigma epsilon graduated. Okay, a problem that raised lots of interest, starting from the 50s, maybe the 60s, is to understand the range of sigma star, how sigma star varies when sigma is allowed to vary in a subset of L infinity. So we let sigma vary in a family of admissible conductivities, and we try and understand how the associated sigma star changes. This is the problem that received lots of attention, especially in the past. It is a difficult problem, and very few cases have been solved. We know the answer only in a few cases that I will show you. So let's see a couple of examples. One case is when sigma is isotropic, which means that it's a multiple of the identity matrix and takes only two values. So it's either alpha I or beta I, and K is the characteristic function of a measurable subset of the cube C, and P is a prescribed volume fraction. Okay, so P is a number between 0 and 1. The G closure, which is the object that we would like to characterize, is the set of all sigma star that we can obtain by letting K vary in the set of all possible characteristic functions. Okay, this is the G closure in the case of isotropic sigma. And the first contributions to this problem are to be found in the seminal paper of Ashen and Strickman from the 62, and an important advancement were obtained later by more or less in the same period by Murat and Tartar in the context of compensated compactness and Lurie and Cherkarev. The solution is known only in 2 dimensions. Okay, so for given alpha, beta, and P, the volume fraction, the solution is this. This is the G closure. Of course, the set G is invariant under rotation, conjugation by rotations. So it's enough to characterize the eigenvalues of sigma star. Okay, so they can be represented in R2. The G closure is a compact subset of R2, and this is the G closure. Another case is when sigma is a polycrystal, which means that the eigenvalues of sigma are fixed, given sigma 1, sigma 2, sigma d, but the eigenvectors are allowed to change from point to point. Okay, so in this case, what is the G closure? The G closure is a set of all sigma star that we can obtain when we let the rotation vary. Okay, R is a matrix field valued in the rotations in SOD. Okay, so this is another problem, and here we have only one case which is solved. So in 2 dimensions, the problem is trivial. One can see that those analyses hold, and therefore the G closure is simply a branch of a hyperbola. Okay. In the case of 2 polycrystals, here there is another typo, I'm sorry. So if sigma is 2 polycrystals, sigma 1, sigma 2, and here C1, C2, okay, different eigenvalues. So it can be, I can have a part of the material, which is the first polycrystal, mixed with another polycrystal, which is the second one, with different eigenvalues. In this case, Frankfurt and Murat show that the G closure is a set like this, but P is arbitrary. So this is the set that one can obtain by letting P vary between 0 and 1. For fixed P, it's infinite. Okay. And these are the only cases that are solved. Okay, that are solved. All the others are over and are partial answers. And now we come to our problem, which is the 3-dimensional polycrystal. This is the problem from which the differential inclusion originates. So now we are in 3 dimensions. We are given 3 positive numbers ordered like this. Sigma 3 is the simplest, and they are all distinct. The G closure, again, is a compact subset of R3. It's enough to characterize only the eigenvalues because the G closure is invariant under rotation. Okay. And the first bounds are the elementary bounds that you see on the first line, which says that the eigenvalues of sigma star should be larger than the smallest of sigma, which is sigma 3, and less than the largest of sigma, that is sigma 1. And this comes that this can be easily obtained by using the ellipticity of sigma in the variation problem. And then there is the other bound, the trace of sigma star. So this is not for the last version, corrected. The trace of sigma star is less than the trace of sigma, not of sigma, okay? So read trace there, which is a number, sigma 1 plus sigma 2 plus sigma 3. And those 2 bounds together, so the black and the blue, say that the G closure
is a subset of R3 lying inside this cube with these vertices, the first, and on the other side of this hexagon. So trace of sigma star equal to the trace of sigma is the plane that intersects the cube in this hexagon. Okay, so the set lies on the other side between this hexagon and then it's inside the cube. These are a metric bound. And then the first non-trivial bound, lower bound, another an additional bound which is not trivial, is the one in pink, framed in pink, which was obtained by Avellaneda, Cherkaeff, Lurie, and Milton in 88. And this bound says that sigma star satisfies that inequality. The determinant of sigma star minus theta squared trace of sigma star minus 2 theta cube is larger than or equal to 0, where theta is the only positive solution of this cubic equation. Okay, determinant of sigma minus etc. They proved that bound. And what does it tell us? It says that if you take the equality, the equation describes this surface, a surface that lies on the other side of this hexagon. So now, since it was impossible to draw it here, I rotated, and this hexagon now is here. And the surface, which is a compound surface, which is like this, becomes this pink one. And this surface intersects the hexagon only at the vertices. So it cuts the cube on the other faces of the cube here. So this line that you see are here on the other faces. Okay. So overall, now we know that the G closure lies between this hexagon and this surface. And the question then was, once they proved this, they knew that all this hexagon is attained. This hexagon belongs to the G closure. So the question they posed was, which points of the surface actually belong to the G closure? Are there points on this surface that belong to the G closure? And in a paper by Enzo and Milton, shortly after, they proved that in fact there is a large portion, by large I mean of Haus's dimension 2, of this surface that actually belong to the G closure, and it's a set which appears more or less like this. Okay, so they show that the lower bound means that the equality is achieved. Okay, what are the sigma stars for which the equality holds? This means that you attain the bound, and you are on the boundary of the G closure. Okay. And so they show that all these points here in darker pink belong to the G closure. So how did they do that? I explain a bit this so that you understand where the differential inclusion comes from. It comes precisely from this. So that's the lower bound, framed in pink. That bound comes from considering this quadratic form. Take this quadratic form, where we have the first term is equal to this first term on the right-hand side, and this is the variational problem that defines sigma star, right? Now we subtract twice theta. Theta is the famous theta, is the positive root of the equation that I showed you. The second invariant of A. The second invariant is a quasi-complex function, a quasi-affine function. It's like determinant, which means that when you move that term inside, you keep the equality. So A is the boundary, is the average of the gradient of U, right? Gradient of U is something periodic plus A. So it's the average of A. And I2 of A is equal to the integral of I2 of grad, okay? This is very important. And now you define the quadratic form that you obtain by adding these two terms. You have an equality. And what Lurie, Cherkaev, Milton showed is that for that choice of theta, this quadratic form, this is the quadratic form that appears in the integrand, is positive semi-definite. So there is a non-trivial null eigenspace. If this is true, also the quadratic form on the right-hand side, which has exactly the same structure, but the coefficients of this quadratic form that you need to imagine like a 9 by 9 matrix, okay, depends on sigma star. Okay, this depends on sigma, the entries of sigma, this depends on sigma star. If this is positive semi-definite, this is also positive semi-definite. Okay, and if this is zero, this is zero. If and only if this quadratic form applied to A is zero, where A is the average of grad U, right? So when do we reach the bound? When do we have zero there? We have zero when the pointwise, the gradient belongs to the null eigenspace of the quadratic form, okay? And so the lower bound is attained if and only if the gradient of U belongs to the null eigenspace. And when does this happen? Well, this is a simple computation. This happens when pointwise the gradient of U has this form, okay? It must be equal to the trace of grad U times this matrix. And now if you define S like this, so you obtain S from here, you write this as a matrix with the rotations on the left and on the right. This means that the gradient of U should take values in the set that I gave you in the beginning, okay? S, because of the definition, because of the assumptions on sigma and the definition of theta, is a matrix whose trace is 1, okay? And the eigenvalues have the reverse ordering of sigma I. So S1 now is the smallest and S3 is the largest. Okay, if the gradient of U takes values in that set, then the gradient of U is an eigenvector with eigenvalue 0 of the quadratic form, and I have the equality in the bound. I attain the bound. But if this happens, then also the quadratic form applied with coefficients sigma star applied to the average of the gradient of U, which is A, is 0. And when is this 0? When A, simple computations, has this form. Okay, so the average of the gradient of U must have that form. So if I divide A by the trace and I call this matrix S star, S star is equal to this. And because of the bounds, the cubic bounds that we had on sigma I star, the eigenvalues of S star satisfy this, okay? To lie between S1 and S3. So what does it mean on this? Summarizing, it means that if there exists a solution of the differential inclusion, gradient U in K, such that the normalized average, normalized I mean we divide by the trace, the normalized average of the gradient lies in that interval, otherwise it's not physically acceptable. This is true if and only if the matrix sigma star there, defined in that way, in terms of S star, which is this, belongs to the G closure, to the bound, to the pink surface, okay? And vice versa. Okay, if I have sigma star, then S star that you can obtain by inverting that formula. That's a one-to-one map. You invert that formula, you obtain a star. A star is a realizable average for a gradient that satisfies the differential inclusion. So this is very convenient because now, instead of trying to understand which matrix belong to this curved surface, we work with S star. S star lies in this hexagon, okay, and no longer on a curved space, curved surface. So this is the hexagon of vertices S1, S2, S3, and all of its permutation. So now the goal becomes find all possible S star that can be realized, that can be the average, the normalized average of gradients that takes values here, here, here. Only these values and all of their rotations and multiples. I will say this again. We are not really interested in exact solutions, so we do not need gradients that takes exactly those values, but they should take values close. So what we look for, in fact, are approximate solutions, so-called approximate solutions, which means sequences of maps, Sobolev maps in our space, that are equibounded in L2 and also L2 equiterable, and such that the distance of these gradients from the target set goes to zero measure. This is enough. We don't need exact solutions. Okay, if this happens, then the average of these gradients provides an admissible S star, and therefore the corresponding sigma star belongs to the boundary of the G closure, to the pink surface. It will be a point in the G closure. Okay, so we call K star the set of all such A. Okay, and this is related to the quasi-convex hull of the set K of S. Also,
Or is the same? Is it related or is the same?
What?
K star is not a quasi-convex hull.
It's not precisely the quasi-convex hull. First of all, because we can only accept averages that whose eigenvalues lie between S1 and S3, so there is a restriction. The other points in the quasi-convex hull are not physically acceptable. And then, since K is not a bounded set, this is unbounded, then the notion of quasi-convex hull is a bit different. Okay, the proper notion of quasi-convex hull related to this is called the two quasi-convex hull. Okay, the two quasi-convex hull.
It's not a compact set, so it's
No, because it's unbounded. It's a double cone. K is a double lambda can be any scalar, so it's unbounded. And in this case, there are different notions. Okay.
But then also your K star would be a double cone, right? Right.
Yes, but we can only describe a section because once a point is there, the whole line is there. We are interested in the section trace is equal to 1. Okay. So we are interested in representing on the hexagon the normalized eigenvalues of these matrices. And by normalize, I mean after we divide by the trace. Trace is equal to sum equal to 1. Okay. So this is what we are looking for. So now you can forget about sigma, you can forget about the space, the pink surface. We have our hexagon, and the hexagon is to be understood as a quotient space. So each point T on this hexagon of vertices S1, S2, S3, and all of its permutation represents a full orbit, which is this, right? So this represents infinitely many matrices. Okay, and once I have T, I have also its permutations. So all these 6 points, because the set is rotationally invariant. Okay, the permutation is a rotation, a particular rotation, right? So I can obtain all of that, all 6 of them. Okay, and so the Enzo and Milton rewrote the problems, the sigma problems, in terms of S and S star, and they formulate this differential inclusion, and they exhibited a class of solutions to this differential inclusion. So they showed that this triangle with the arms belong to the G closure, so belong to K star, and therefore the corresponding sigma star belong to the boundary of the G closure. And not only this triangle, but also its mirror image. So here I do both the triangles with their arms, okay? So they show that this set belongs to the geometry. And they do this by exhibiting approximate solutions using these infinite rank laminations. And for those who are familiar with this construction is reminiscent of the Tartar square. And so in order to appreciate this, I will digress. I will make a short digression about these infinite rank laminations. How do we construct gradients that are approximate solutions? So this is the basic construction of the convex integration. Suppose we have two matrices, S1 and T1, that are rank 1 connected. So the rank of S1 minus T1 is 1, which means that their difference can be written as the tensor product of two vectors. And since we are in the symmetrics, we are dealing only with symmetric matrices, these two vectors are the same. Otherwise, we would have A tensor B. But here we have N1 tensor N1, where N1 is a vector in R3. Okay, this is always true. If the rank of the difference is 1 and the two matrices are symmetric. In this situation, if A is a convex combination of S1 and T1, then there exists a map U, a Lipschitz map. In fact, we can choose also 0 here. Okay, so have affine boundary condition AX, such that the distance of its gradient from S1 and T1 is small, can be arbitrarily small. So for each delta 1, I can find U1 such that this is true. And this gradient can have any average between S1 and T1. Okay. Then suppose that T1 can be splitted, can be written as the convex combination of two matrices S2 and T2 that are also rank 1 connected. So there exists another vector N2 such that this equality holds. If this is true, then I said something. So how do we define these geometries? With layers. So this U1 looks like this. U1 is as gradient as 1 in this strip, T1 in this, and these layers are orthogonal to the direction N1 that appears here. U1 is a small variation of this. Okay. If I can split T1, then I can replace T1 by a lamination of T2S2, T2S2 in layers orthogonal to N2, which is that vector. Okay, so I can construct now a map U2 with the same affine boundary condition A, the one that I fixed in the beginning, which was an element between S1 and T1. I can find U2 whose gradient is close to S1, S2, and T2. So T1 has disappeared. And then I can iterate this procedure. This is called splitting, a splitting procedure, as long as I can split the last one into two rank 1 convex matrices that satisfy certain properties that I like. So by iterating this procedure,
that ds in W1 infinity is for periodic, no?
yes, you can get 0. In fact, this can be 0 here. I mean, U2 minus AX, W1 0. Okay, so you can iterate this procedure, and in the end, we can construct a sequence UN that satisfies this. So the idea is, so they applied this construction by using matrices S1, S2, Sn minus 1, which are in the target space, K of S, okay? So they are a multimodal of a rotation of S, okay? And then there is always a last bit where the gradient is close to the wrong matrix, Tn, that they call seed material. So, no, let's go back. You start from that vertex, S, call it S1. You laminate with this point, call it T1. And when I say this point, it's not precisely this point. It's a point in the orbit. And then they split this point between this vertex, which is good, because it belongs to the set, and this other. And then you replace this by a lamination of this point, which I like, and another. And then you go on like this, okay? So it's not a closed loop, because it's like a staircase, okay? These are unbounded. In LFE, they are unbounded, these sequences, okay? And, but the point is that the set where the gradient takes values, one of these 3 points, so values that I don't like, is a set whose measure goes to 0. So I make this modification, this splitting in sets of measure that is smaller and smaller. So this is the way that approximate solutions are built. And this is the basic construction of the convex integration. So this is what they did. And this is how they obtained these 2 triangles. And the union of these triangles with the arms belong to the G closure, belong to K star. Okay? Okay, now, so what do? We improve this bound. So we show that there is a larger set that includes the Miltonese set. So there are other points also that are attainable, realizable, and which can be obtained with a more complex construction, but always based on this splitting, on the splitting procedure. So in the construction of Miltonese, these lines are rank 1 lines, right? They are the projection on the hexagon of the rank 1 segments connecting the matrices. They work only with diagonal matrices. In order to improve this bound, we need to depart from the diagonal world and use all of the matrices, the symmetric matrices. Okay, otherwise we cannot do better than that. Okay. So the main feature of these lines, these rank 1 lines appearing in their construction, is that along these trajectories, so when now I say rank 1 trajectories, I mean the projection on the hexagon of these rank 1 segments, which live in a larger space, right? These are just projections. Along these trajectories, there are 2 eigenvalue crossings occurring. You see, you start from S1, S2, S3, then this is a uniaxial axis, which means along this line, the first and the second eigenvalues are the same. S1 is equal to S2, okay? So there is one eigenvalue crossing here, and then after a while another eigenvalue crossing occurring. The second and the third coincide. So I start from S1, S2, S1, S2, S3, and I end up at a point where the first eigenvalue became the smallest. And this is an essential feature of these constructions. And all constructions, all rank 1 trajectories enjoying this feature, so experiencing 2 eigenvalue crossing, are this. There are no others. Okay. So in order to improve the bounds, we look for trajectories, rank 1 trajectories, that only experience 1 eigenvalue crossing. So we look for trajectories like this. Okay, so this is, guys, a topic point, right, where all the eigenvalues are the same, 1, 3, 1, 3, 1. So you see here, along this trajectory, we hit this axis, and then we end up here. Okay, and not
By trajectory, you mean these
rank 1 lines. Yes,
Exactly.
rank 1 lines. So
So
these
each-
are rank 1 trajectories.
So each of these is a
Like
union segment.
the volume fraction you let it vary from one to another.
Sorry, these are the projection on the hexagon of rank 1 lines connecting multiple of and rotated S with some point.
Yeah, so they are topological, is why it's linear lines.
No,
In the
the trajectory comes from the fact that you use a volume fraction. So you start with you take these two matrices and you allow all the possible volume fraction going from one to another.
Yeah, I take the rank one segment and then I project it. And now the curves are curved. They are no longer segment because these are not diagonal matrices. So since I'm representing the eigenvalues of the convex combination of two matrices are not the convex combination of the eigenvalues, as it was for the diagonal matrices. Okay, this is why now these lines are curved. This they will always be curved because these are no longer diagonal matrices. Okay. So, and what are the now the trajectories that we want to use? We need not only this, that they have an eigenvalue crossing, but that if you end up here at this point, T2, T1, T3, along the trajectory, you should traverse the point which is the mirror image of this. Okay, what does it mean that this? It means that, so these are the trajectories that we are interested in, we are looking for. This is the segment that starts for t equals 0 is lambda s, multiple of s, okay? And here you can take s diagonal because you can put the rotation either here or here, is the same. So you start from lambda s and then you let t run between 0 and 1 and you end up here. So you start from s and then when you project this, you only represent the eigenvalues, you end up here. Let's say that you started from here and you end up here. But there is a t, some t tilde. For some t tilde, this segment contains an object of this form. You see, same eigenvalues. Rho is a scalar, so it disappears. When I project it on the hexagon, rho is not there, the rotations are not there. Okay, so along the segment, I meet a point whose projection is here. And this is the mirror image of this. So they have the same eigenvalues, but permutated. The first and the second are both. Okay, so these are the trajectories that we find. And why this? Because, first of all, they are higher of the trajectories of Milton-Nesi. And of course, we need to be able now to implement this scheme, the infinite rank lamination. And we are able to do this precisely because there is this point. So here I drew two examples of such curves, the black, and here also there is this, and the mirror image, and the blue, okay? And if this happens, we are now, the picture is, I cannot make a two-dimensional picture, so I attempted a three-dimensional picture, but we are in 5 dimensions, right? 3 by 3 symmetric matrices. So the idea is that you start from some S1, which is a multiple of S. This is connected to this T1. And along this trajectory, I need a point whose projection is this, mirror image. If this happens, then I'm able to find S2, which is in the target set. So the projection of S2 is a good point. And from here I find, so I can split T1 between S2 and T2. S2 is good. T2 has projection here. And then I can iterate this. So having these pairs of points allow us to implement the scheme. If this does not happen, we wouldn't be able. So, the construction then continues, but I couldn't draw more. And these are unbounded. There are cases where they are bounded and cases where they are unbounded. But they are bounded in F2, equibounded in F2, the gradients, and also equiintegral both.
But the construction should start from the T, right?
You start from S1 and T1. Then you take T1, which you don't like, you split it into S2, which you like, you keep, and T2. Then you don't like T2, so you replace T2 by some S3.
So in some sense, the procedure should be to give it T2 now. You have to find a sort of S3 and
Yes,
T3
I will find S3 and T3, and then I
curve
can
which
T3.
is passing with this property.
Yes, yes, and all these segments that here I drew in a random way. Okay? I drew in a random way. So you obtain something like this. And when you project all these rank 1 segments on the hexagon, no, see, no, it's very confusing this. When you project all these, no. When you project all these segments, you always obtain the same curve. The projection is always the same. So take the black one, it's always this, the projection, it's always this. Of course, you could use other vertices. It's the same.
One of the steps.
One of the steps, it's always the same projection,
Ah.
always there, always there. So I couldn't draw a two-dimensional picture because you would not have understood.
But you start from an S, which is the projection of the S2.
You take S1, S2, S3. You
Yeah.
could restrict to the first sextant, in fact.
Mhm.
You don't need to use the whole hexagon. It's enough to use one sextant, and then, of course, you have also the rest. But it's convenient to have more space. Okay? Okay, now, all these trajectories belong to the G-Lodge, to K star, the set that I called K star. What is the best trajectory that I can get? What is the highest? The closer the final point is to the uniaxial point, the better it is. And in fact, the best point is U, is the uniaxial point where the first and the second eigenvalues are the same. So I take the trajectory starting from S and ending in U. That's the best trajectory, and that will be the boundary of our inner bound, new sense that we find. Of course, we cannot make this construction directly for you. We cannot do this splitting because there is no space to split. So we recover you only in the limit.
So they coincide. That's okay.
Yes, they coincide. So I don't have space to move, but it doesn't matter because I recover that with a
Yeah.
closure argument.
Approximate solution.
Yes, approximate solution. Okay, so this is the set that we obtained. Of course, now I only worked with these trajectories where we have the eigenvalue crossing 1, 2. But in fact, there is a lower branch where I have the other eigenvalue crossing. The second hits the third. Okay, so there I drew the sextant. So you should just look at that sextant. And our new bound are the green lines. Okay, and they improve the previous set. The previous set, Miltonesi is the one there. And the new points, the additional points are the ones in orange. Okay, so this is our new set. So now you take this curve and then you permutate, you reflect, and you obtain this set L of S. Once you know that those points are there, you have all the points in the X. So this is our new bound. And we don't know whether this is the optimal. We don't know whether there are points outside, but we can say that by using this method, we cannot get anything else. Okay, this is the best that we can do. And what we like of the new set is that this set, in contrast to the previous one, Miltonesi, enjoys a property which is called the stability under lamination. What is the stability under lamination? It means that if I have 2 points inside L, our new set, and they are rank 1 connected. So what does it mean that they are rank 1 connected? There exists a multiple of T1 and a rotation of conjugate of T2 such that the rank of this difference is 1. Okay, these are just the projections. So there exists something in their orbits that are connected. Well, if I take this segment now and I project, and this is the projection, this lies inside the set. So the projection on the hexagon of this rank 1 segment lies inside, does not exit. And this is an important property that we would obtain for free if we knew that there is no other element outside, that this is precisely K star. But since we don't know, then we needed to prove it by hands. Okay, and it's important from an application point of view because it says that if you have two materials, two sigma stars in the G closure, and you mix these two materials, you are not creating a new material. So this is the interpretation of this mathematical property. So how do we prove it? Very quickly. We want to rule out these cases, right? We want to show that this is not possible. Okay? So we can, first of all, reduce to the case where the pair T1, T2 belong to the same branch of the curve. Why? Because if I have a point here and then the point there, then the rank one trajectory has to pass through this point by convexity because it has to lie inside the hexagon. And so I can break it into two. So from here, say, to here, and then to here, here to here. So we can reduce to this case. We just need to focus on this. And how do we rule out this case? With a geometric argument. So what we do is we compute, take this rank one trajectory. We want to show that it lies inside. It starts from T1 and then up in T2. We compute the slope, we compare the slope of the tangent to this rank one trajectory and the tangent to the optimal curve. Okay? And but we do not use the variables, the Euclidean variables, but we use new variables. We express all the quantities in terms of the second and the third invariant. The third invariant is the determinant. The second invariant is the product of pairwise product of the eigenvalues. Okay, these allow us to get rid of the rotation. Otherwise, it would be very, very complicated. It's already very complicated. It's 10 pages to add the formula for the slopes. So, doing this, we are able to say that this tangent points inwards. Okay. And so we are able to show the stability under lamination. So this is what we have done. And now I conclude by mentioning some open problems, which are interesting also independently of the polycrystal applications. First of all, we don't have outer bounds. We are not able to say whether there are other points outside L that actually belongs to K star. And this is related to the lack of the fact that we do not have many available quasi-convex functions. Quasi-convex functions are tools that provide bounds, outer bounds in these kind of problems. And known quasi-convex functions are very few. It's basically the determinant and variations of the determinant. But these that are known do not provide a meaningful bound. So this is the first. And we do not have outer bounds, not even in the uniaxial case. So recall that in the beginning, I assumed that sigma 1, sigma 2, sigma 3, and therefore S1, S2, S3 are all distinct. What happens? Otherwise, we cannot make this abstraction. But in that case, in the case where two eigenvalues coincide, either the first two or the last two, these cases can be obtained as a limit case of ours, but they were already known before. Okay, so the known points, realizable points, are simply these segments, right? The hexagon reduces to 3 points because two eigenvalues coincide. So either it's there or there, in this case. Not even in this case, we are able to rule out points outside these segments. And so far we have talked about approximate solutions. Are there exact solutions? This would be also nice to understand. The only exact solution known, which was already known, and here there is the other typo because there is not the name appearing, is an exact solution in the uniaxial case, either that or this, for this point, for the isotropic point. This function has gradients that takes values in the right set. So alpha is given by either this or that, depending on whether the first two or the last two are the same. And the average of that gradient is this point. So this is the only point, this or there, for which an exact solution is known. We don't have any other. And it would be nice to say that whether to exhibit some other or to show that they do not exist, to have some rigidity result. We don't have them. And finally, if we had exact solutions, then these exact solutions would be weakly L quasi-regular map. What does it mean? A map is L weakly L quasi-regular if it satisfies point one is this inequality, where this norm is the operatorial norm, okay, the operatorial norm of the matrix, value at X. And the cube is the dimension, okay? And for some constant L larger than or equal to 1. And in our case, L would be this, if there were exact solutions. And this is interesting because in a paper by Jan, he shows that if L, this constant, is sufficiently close to 1, which means that in a certain range of S1, S2, S3, then there are constraints on the boundary conditions. Not all averages are admissible, okay? So there are some further conditions. So we would be able to rule out some points, okay? But this is true also only for exact solutions. So the question is, which is a very interesting problem, I think, is there any rigidity result like this, but for approximate solutions, which means that maps that do not satisfy that almost everywhere, but the set where they do not satisfy inequality has measured and goes to 0. So they are approximately satisfied. Yeah. So this is an open question because I searched a bit and I talked to someone, they say, we don't know. We don't have any such result. And with this, I conclude and I thank you all. No, there is another slide. There is another slide. So this is okay, very, very quick. This gradient, if we have exact solutions, K's are all symmetric matrices. So can we infer something from the symmetry of the gradients? Because if I have a symmetric gradient, this is the action of something. There is a potential, right? We have never used this, but this is important because it gives structure. So if the gradient of U is the action of something, then if we satisfy this, and you see here, this is the Laplacian, which was the trace of the gradient, times this. And so you see, we have an action which is either 0 when the Laplacian is 0, or if it's not 0, it has full rank. Is this possible? Which kind of maps tree can satisfy this? Maybe one can prove some rigidity results for these kind of maps. And now I really think that it's all. Thank you very much.
Do you have any question, comment, or remark?
About the open problems, no, and in particular the possibility to look for exact solution. No, first, did you make some numerical simulations or something?
No.
And then second,
I'm not able.
this is the typical context in which the new deep learning business should come into play. Do you know if somehow
Declare what?
deep learning,
What is it talking about? Some program?
this is a business related to the use of, let's say, artificial intelligence?
No, I have no idea. I have no idea.
I mean, it's strange to me, no, that.
Well, you need material to train that artificial intelligence. Okay, it's an old file, but I don't think there is enough material to train.
But in these simulations, there is always a margin of error. So how can you get an exact solution? Or okay, I don't know anything about
This
this.
is the point. I mean, it's to involve the computer in the business.
Well, it was already worked in the sense that we guessed this microstructure by computing, but we were using the exact formula that come from this sort of lamination formulas, which are an example. So we didn't do the full. So I think you're right, but we are not. We don't have that.
But are engineers doing that, or?
Are there still applied people who are doing this?
No, but I mean, okay. So I can tell you that some of this microstructure have had some. I mean, people are interested in exact microstructures, Graham has made this, for instance, some very surprising results in classical Hall effect by constructing materials. We have a very unexpected physical behavior. But this, if you do it blindly, I think it's very hard to get anywhere. So I think your idea is right, but one would need to really train people who have tried numerical simulation for years is going nowhere, because there are literally infinite many possibilities. At each step you can do, and there is so, and to find the exact solution is very difficult. Because as soon as you do an interface, the structure becomes extremely, and the solution becomes extremely singular. All these things, I shouldn't say that, but all these things have these problems have originally a higher integrability property. So the gradient is a bit better than F2, but these solutions do not. They get test worse as experiment. So I don't know if there is somebody doing this, but I don't think there is any. Nobody has made any progress on it. Sure.
I will be, I mean, we will make some head. I have no idea.
So we have a quantum computer here in San Sebastian, so if you need it.
You need to invite us again. Okay.
Thanks again to Megan. Okay, now the last but not least speaker of the day, and also the workshop, official speaker of the workshop, is Emanuele Spararo, Nuncio, for the friends. From University of Roma La Sapienza. Okay. The title of his talk is On the Measure of the Branch Set of Minimally Measured.
Okay, thank you very much. I have to thank the organizers. So but a lot of value. An amazing day. It's really a great opportunity to celebrate this event here. That's really pleasant. And also, I didn't prepare, but I want to say something to friends. I think we met, so this morning we were sort of reconstructing. Surely we met when I was in Zurich during my PhD. But I remember him in Rome for a conference. I was visiting Rome. It was around 2008 or 9, I don't remember when. And I met Enzo. He was very, very kind to me. And I remember at that time, he was saying, perhaps in the future you would like to come to Rome, consider contacting me. He was perhaps the first one to prospecting this. And in the end, I went to Rome, so thanks for these ambitions, for this vision back then. And when I went to Rome, Lorenzo was very busy with, I think it was not anymore, dean of the department, but was dean of the faculty. So the first years I didn't interact very much with him. But then I met him in the class. We were teaching on parallel sections of the same class. And since then, I have to say, I've really learned a lot from it. Both, for the teaching, and also, for the way, of looking at problems, and from the taste of the problems, and in the end, we end up doing also a collaboration. But I also learned that our role at university is not only a technical role. You need to have a vision. You need to have, you need to see, things from a perspective which is not from the bottom, but to embrace, in some sense, all the, how do you say, all the reality. So that's, thanks a lot. I really think I've really learned a lot in these last years from you. So thank you very much. And today, so I didn't want, to make a standard talk, but I wanted to talk about something which may have relation with the things we have been studying together. Try, I mean, to point out links and so perhaps also for future collaboration. So I will go back to the project with Enzo, Eugenio, and Flavia, but I will attack it from a geometric point of view, and I will talk about minimal meshes. So the topic is the one of minimal surfaces. So we are looking at geometric objects, let's say n-dimensional. I should talk some manifolds, but they will never be some manifold. But let's keep in mind this.
Oggetti sono vicino allo schermo.
Ah, ok, grazie. E I will explain why. I mean, we are not interested really in some manifold, but we have an idea. So that's the point, where the mean curvature is 0. It's usually indicated by h. It's the trace of the set fundamental form. And the equation, I mean, behind this object is 0. So in general, we can look at n-dimensional submanifolds, let's say in R, n plus k. And k is what we call the codimension. So n is bigger or equal than 1, but okay, let's consider at least surfaces. And k can be bigger or equal to 1. Now, let's start with examples. This sort of theory is very different if one looks at codimension 1 or codimension bigger than 1. It really separates. So the codimension 1 case, on the codimension 1 case, you have, and I mean, let me say, now we are to this. I mean, there are some manifolds because we are looking at singularities of this solution. And in the codimension 1 case, the singularities we realize are cone-like singularities. So a prototypical examples of a minimal submanifold, codimension 1, which is not a submanifold but has some singularities, is the Simon cone, which is a set. We'll describe it as a set, but of course it has much more structure in R8. Which is the one you will draw exactly as a cone. So x1 plus x4 squared equal to x5 plus x8 squared. So if you put 4 dimensions of the horizontal part and 4 in the vertical part, so that's in some sense the set, you see. And you see this point as a singularity, but in some sense this point has no tangent plane. So the tangent plane and here is not defined. On the other hand, if you look at codimension, at higher codimension, so singularities, of course, you can find also this kind of singularities. But in some sense, there are some new singularities. And the prototypical examples of something which may be seen as a submanifold, but with singularities, are the complex varieties. So, for example, we can take a complex curve in C4. So let's call V. For the set Z. So in R4 in C2. So ZW in C2 such that let's say W squared is equal to Z to the third. So that's coordination, complex coordination 1 in C4, in R4 in C2. And if you draw this again schematically by looking at the modulus of Z and W, it's like having the 2 square roots of Z to the third. So that's a solution we have also encountered in our work. So it's like W should be, in some sense, both determination of the square root. So you will draw this like this. So in which sense are these minimal vertices? In a very strong sense. So both are solution to the plateau problem. So they are, in some sense, the object with the least area given the boundary. So meaning that if we solve this variational problem, which is fix the boundary of this object, so for example, so fixing gamma, which is the Simon cone intersected with the boundary of both one. And if you look at the minimizers, so regular submanifold, having these smooth boundaries, and minimizing sequence or minimizing the area, you don't find a minimal submanifold, but any minimizing sequence for the area is converging to this cone. So we create a singularity here. And the same happens here. You may intend to fix the boundary. So you take, again, gamma will be V intersected with the boundary of the ball in R4. And again, if you look at the regular submanifold with this boundary, which are converging to the minimum of the area, you end up with exactly with this complex stuff. So in some sense, they are the unique minimizers, and it's the only objects you can get by minimizing with these boundaries. Now, of course, you end up, it depends on the topology. And indeed, that's why we don't talk about some manifold, because there is no strong convergence. You have to imagine that if you take a minimizing sequence with this boundary, you have something like this for modulus, so the symmetry group coming from so the rotation in the first 4 and then the other 4 things. And when they converge to this, of course, they do not converge C2 because the curvature is blowing up here. So it's not a smooth convergence. It's a convergence in the sense of measures, in some sense, in a weak sense. So that's why, in the end, singularities may emerge. But what is surprising is that they have to emerge. So the interest, in this context is to understand the nature of these singularities. So which kind of singularity can emerge as limiting of regular minimal surfaces.
When you say they have to appear, it's because you see them.
No, they have to appear because it's you can prove that this one is the unique limit of all possible sequences of some manifolds.
Okay.
So minimizing the area with this boundary. So it's not avoidable in some sense. So it's this one was so discovered by Simon, and the proof that this one is the only minimizer is a famous result by Bombieri di Giorgio Giusti. In 69. And this one was, again, something which was sort of well known. So goes back to Wistinger. And it was formulated in this setting by Federer in the 70s. So what makes these two singularities different? So the first one, you see, I've drawn it as a cone. And this one instead has a flat, as a tangent plane. So it's like, I mean, in this picture, when I draw the modulus of W and the modulus of, as a function of the modulus of Z, that's the power 3 So it's differentiable, continuously differentiable, and it has a sort of tangent plane here, which is flat. Infinitesimally, it looks at flat. And that's what makes these two problems very different. And indeed, the results are very different. And what are the results? So for four-dimension one case, if we look at the dimension of these singularities, this one is the optimal one. So the dimension of the singular set is less or equal than n minus 7. And you see it corresponds here. So this one is another surface. It's one equation in array. So it's a 7-dimensional object. And the singularity is 0-dimensional. It's a point. And this one is a very long achievement. I mean, starting from, let's say, George, Federer, and many others. In codimension 2, the dimension of this singular set changes. And it becomes n minus 2. So you may have singularities already for surfaces, which is what happens here. It's a complex car, so a two-dimensional real object, and the singular set is a point. So the dimension of the surface is 2, and the singularity is a point is 0. And of course, these bounds are sharp, because it's also in any dimension, doesn't consist, because any solution you can extend constantly in the extra direction, and the mean curvature is not changing. So the equation is satisfied if you extend constantly in the other direction. So what about sort of the structure of these singularities? Now, in this case, there's been a couple of impressive results. So one sort of very recently is a result by number in Bartorta. So around 2016, which says that not just the dimension of this singular set is n minus 7, but also the measure of this set is finite. So the measure should be the n minus 7 dimension 1, which is denoted by the out of measures. So the measure of these singularities, which can appear there, is locally on every compact set, it's finite. N plus 3. And there was a result. So this one was coming out from a very interesting work by Leon Simon in the 90s, where he was proving that this set has also a structure. So it's what is called rectifiable. So the singular set is n minus 7 rectifiable.
Excuse me, this is true only when n is larger or equal to 7.
Only, otherwise it's empty.
Otherwise it's empty, yeah.
There are no singularities.
Okay.
So the first singularities appear in array. There is this dimension, there is no singular solution. So for example, all the classical solution to the plateau problem in R3 are regular. It's an outcome of this result. when they appears, they have a structure. So if you don't know, so what is rectifiable, it's like in a weak sense, they are a submanifold. So for example, in zero dimension, there are points. Where they are one dimensional, they should be contained in curves and so on. No? So they have a geometric structure, which does imply, to be finite, but they are also finite. Now, in higher codimension, this result is due to 100 and came much later. You have to think this one was concluded in the 70s, and this one is actually it's a paper which was published in 2000, so after Almgren was dead. Because it's a paper, so to speak. It's now it's published. It's a book of 3,000 pages. That's a proof of this result. And now, there are various groups working on this problem, trying to understand the structure of these singularities. And very, very recent result, not yet published, but of last years, there are two groups. One is one by Camillo De Lentis and many collaborators, which are, I don't remember all the combinations. And the other one is Krummel, Vikramasekera. So they proved that the singular set is rectifiable. So again, has the structure to be contained in some manifolds. And what is pretty often is the question on the measure of this singular set.
Let me understand, so the rectificability property is independent of the codimension, no? It's a kind of...
It's independent of the condition. Just mean we contain on some manifold with the right dimension. And the dimension is for everything is n minus 2 in this case, n minus 7 in this other case. So the result I will present is to do with this, with the case of, it's a result on the measure of this singular set. And now, so these are the results. In some sense, gives you a hint why these two problems, are different. Because they have very different results. But let me explain you better this. So from a point of view of geometry, so why also the techniques are different.
At the beginning, you thought something about the relation with the segregation problem. So it's
Yes. And, perhaps I can immediately go on this. So let me go on this point. So let's keep in mind the picture of the complex curve and recall, the problem of Flavia on the segregation problem. So the thought of Flavia. Remember, so Flavia was looking at maps which were written as a sum of n density, which were separated and all positive. Now, if you look at the graph of this U, so which are the points x, u of x, and if you take also minus u as a function, so the trivial operation, if you also take the minus u, and you take the union of the two, now this one is not a minimal surface, but almost. So this is the picture. You have, you remember the solution was a continuous gradient around the singular point. So now here, so which in the fall of fire, the singular points were this. So where more than two species were existing. So I put this point here. Around this point, so the derivative was continuous. They were behaving like at least z to the 3 alpha, and I mean it's not the case. So you can picture u like this. So that's u1, u2. So this one is the graph of u, and if you double it and you take minus u, so locally you obtain the same picture as that. And indeed, the infinitesimal model for this singularity and that singularity is the same. So here, Flavio showed that locally around this point, so the solution behaves like a complex power. So here, the solution U is like the real part of the complex power set to the alpha, where alpha is an alpha integer. And if you look at the minimal surfaces in hyper dimension, at least in dimension 2, so let's say here you have the complex plane, here you may have sort of whatever codimension, but also here the local behavior is like being either the real part if you have codimension 1 or I mean vector value or whatever, but the local behavior is again z was z to the 3 half or any power of z. And in which sense this one is enormous minimizers, enormous minimal surfaces, in the sense that this surface now is stationary for the linearized version of the minimal surface. So this surface here, it's sort of is stationary for the Dirichlet energy. And you remember the problem that Flavio was pointing out was a minimum problem on the Dirichlet energy of you, which sort of it takes the same phenomenon of the minimal surface energy. Now we come to the results, which I mean will create this link for evidence. So the case we have considered for studying one instance of this problem of the measure was exactly this. So was the case in which the minimal surfaces was parameterized as a double graph. So we have considered what we called two-value graph or two-value function. And this one is the link between the problem Flavio was talking about and the result I'm going to present. So this one are functions which are coming from, which goes from a domain let's say omega, a domain in Rn. This one is the dimension of our object. And instead of giving a single value as it is for common function, we give to this, we assign to these two values. So u1, u2. But this couple of values has to be meant as a set. So in some sense, here I cannot distinguish which is the first point and the second point. So to the set of 2 points we call A2, and it's sort of the set of 2 Dirac deltas. You may imagine like this. So you take the sum of 2 Dirac deltas, where the point P1, P2 are in K. So you just look at the support of the pressure. So which is the first point, which is the second point, you cannot distinguish. Or, I mean, if you want, you can imagine like Rk times Rk by the equivalence relation of the permutation of the two. And in this way, you can parameterize, for example, the solution of the problem of Flavia, or you can parameterize the complex curve I've written to you. Because the solution of the problem of Flavia is parameterized by map, which is assigned u and minus u at each point. The solution of the complex curve is parameterized by the map, which sends zeta to 1 square root of zeta and the other. So let me write this approximately like this. And the object we look at are the graph of this multiple rate function. So we are interested in gamma, which is the graph, let's say this function u. So that's the graph of u, which are the points x, ui of x for both branches. So that's, in some sense, a way to write analytically as a graph of the function, a double covering of a plane. Now, for this map, you may define energies. And the energy in the case of Flavia is exactly the Dirichlet energy. So this one for Flavia was 1/2 the integral of the energy of du1 plus the energy of du2. In the case of minimal surfaces, you look at the area function. So, for example, what we do, I mean, also works in codimension 1. Otherwise, I mean, I have to write let me write the general formula. So that's the square root of the determinant in let me write in codimension 1. I mean, that's the area function is the square root of the determinant of a combination of the minors for the first branch and for the other branch, where this P of M is I plus M transpose M. Okay. In codimension 1 is the usual area function. So the only difference between the two problems, in some sense, is that the objects we consider are stationary for this functional. The problems Flavia was considering were stationary for this. And now the questions are the same. I mean, what can we say about the singular set? And now let me turn to the conclusion. So the singular set we characterize in the following way. So what I'm going to tell you still adds some information in some sense, which I will try to put by the end. So, but the singular set for such objects are what are called branch points, which are exactly the points which were depicted there, which are the points where the two branches coincide, but also in some sense they have a common tangent plane. So also the gradient of the two branches has to coincide. So that's, let's say, it's the set of range points of view. And what we prove, that's a result with Paolo De Donato, is that locally the Hn-2 measures of the branching set of a solution to the minimal surfaces, which is parameterized by such a graph, locally this one is finite. So this one is the result. Now, so the proof is a bit technical. In some sense, it involves joining together this approach of Andre and Linare Rapporto. So I'm not going exactly to explain, what is behind the proof, but I would like to fill some missing information in this step. And the missing, in some sense, to clarify, so the nature of this statement here. In some sense, the missing information here is the way we treat these functions, these two-value functions. Because the reason why here we give not another couple of functions, but a function in this space of Dirac measures, or in this singular space with permutation, is that actually we can never split in a consistent way U1 and U2 around each point. In particular, so that's sort of final comment to explain why this sort of statement is sort of complicated. So if you look at the map, zeta going to plus or minus the two square root, you see that this one is a two cover of the plane, of the z plane, meaning that around the origin, we can never find a continuous selection. We can never write this function as U1, U2 with U1 and U2 which are continuous. Because every time you start from a branch and you go around, you end up in the other branch. So you have to cut your domain, and your U1 and U2 will be sort of discontinuous there. So if they are discontinuous, how can we define the gradient of this function? So there is a theory on this. In some sense, you never look at the single. That's just an easy way to write this object, but you never look at the single function, U1 and U2. You always look at the couple. So when you define the gradient, so the gradient of U is itself a two-valued map. So, which again, you write like du1, du2, but what you really mean is that when you take the difference between u of x and a two-values function, which is the one given by the linear part of this two part of this, so which we can write like this. And this space is a natural structure, as a metric space. So when you take the difference between the couple and a couple of linear functions, this one should be infinitesimal with a distance. For example, this one defines a unique notion of derivative, which is the one you put inside your function to compute the equation. So in some sense, these one are points, are exactly those points where your solution cannot be split in two regular branches. So it's not the union of two regular surfaces, but it's a singular regular surface which is going around, so twice around the singular point. That's for dimension 2, when n is equal to 2. In n dimension, this picture is not, it's not so clean anymore. So the singularities have dimension n minus 2. So the solution has, in some sense, this structure of singularities like complex variety, but this one is something we don't know. So why I thought this topic sort of could have been interesting, I mean, for you, because in some sense, so the question, it has a sort of many open questions that you can also read in the context of the problem of species. So, for example, in higher dimension for the problem of species, if you change like the energy, like Luca was suggesting, or I mean, if you look at the genericity solutions in more than 2 dimensions, so can you use techniques like this in order to treat 5-dimensional cases? That's an open question. Another question, which I think is it's open, it's going the other way around. If you now look at the minimal image, which has this sort of branch points, so can you find some generic solution in this context? So, for example, it is true that again generically here you find always the power 3/2 and not higher power, which was in some sense basically the result of Flavia. So this one I don't think it's yet known. And in some sense, I wanted to point out that that result on the pieces, I mean, could be read from a geometric point of view, looking at the graph, but not of the graph of the productions, which has, I mean, it's not stationary, I mean, for any sort of function, but as a graph of doubling this solution, where then the singularities are resolved. So the singularities when your solution is just Lipschitz is resolved because you double it, and you are only left with the current branch points, which are the singular points we have been looking for. Yeah. Okay, and stop it.
Thank you very much. There are any comment, remark, questions, so on? If not, they come back, I think.
Sure.
Okay.
No, so just to announce that at 12 o'clock we will have a final greeting by Enzo. So if some of you want to participate, you are welcome. The greeting will be unified channels worldwide. People from all over the world will attend by Zoom.
Ok. Luca, dirò qualche parola io per concludere questo incontro. Prima di tutto vorrei ringraziare Luca, che effettivamente è stato lui il vero organizzatore, penso non fosse un mistero questo. Senza di te non ci sarebbe stato questo evento, diciamo così, è giusto riconoscere. Seconda cosa, tutti i conferenzieri, compreso Luca, che conferenzieri hanno detto qualche parola su Enzo, e quindi lo vorrei dire anche io prima di lasciare la parola a Enzo. Pensavo un pochettino a cosa raccontare, non ho preparato nulla, quindi spero di non commuovermi e bloccarmi. E poi soprattutto ho pensato che per motivi di privacy, diciamo così, non è nemmeno giusto andare chissà quanto nel dettaglio, però facevo questa riflessione. Adesso da un po' di anni che va di moda questo libro che tutti quanti voi conoscete, Il Piccolo Principe di Antoine de Saint-Exupéry, in cui c'è questa frase che con tutte le citazioni un po' avulse poi viene così perde un po' il significato originale. L'essenziale è invisibile agli occhi. E io penso che invece una delle grosse lezioni che mi ha dato Enzo è questa, che l'essenziale non è invisibile, è semplicemente che molte persone non vogliono vedere e quindi lo dimenticano. E la prima cosa che Enzo mi ha insegnato fu quando, per esempio, abbiamo fatto un corso in solitario, che facevamo una discussione sugli esercizi, mi corresso un esercizio, senza entrare in dettagli, che tanto non è importante, e lì per lì mi ricordo ci rimasi un pochettino male perché mi sembrava un po' come una prevaricazione della mia idea, insomma, una violenza in qualche senso. Invece poi niente, come spesso quasi sempre è accaduto con Enzo, togliamo anche il quasi, c'ha ragione. L'esercizio semplificato andava bene e coglieva l'essenziale dell'esercizio. Semplicemente che spesso non vogliamo vedere cos'è l'essenziale nell'esercizio. E poi un'altra cosa che volevo ricordare è questo qui. A un certo punto, diciamo così, della mia attività qui al Castelnuovo, quando uno entra come ricercatore, all'inizio è sempre un po' abbandonato a sé, a meno che uno è più fortunato. Io ricordo che all'inizio ho patito un po' la solitudine, poi le cose per fortuna sono un po' partite, e a un certo punto Enzo mi ricoinvolse anche dal punto di vista della didattica insieme a Lamberto, ad analisi settoriale, a fisica, e mi divertì molto. Quelle cose che ricordi, i compiti dei colleghi li correggiamo tutti quanti, un lavorone piacevole, divertente, ma soprattutto Enzo anche lì aveva capito che così, mi aveva cercato in un certo senso, e perché tutte le persone sanno quando che tu puoi ignorare una persona o meno, e Enzo non mi ha mai ignorato. Infatti concludo subito perché non voglio rubarti spazio, Enzo, però il mio ringraziamento è questo qui, perché non per quello che ha insegnato, per il direttore, per il preside, ma per la...
Allora, sì, io devo scusare, ma non sarò breve, perché oggi devo essere egoista e prendermi questo tempo per raccontarvi molte cose. Comincio con un saluto che però faccio citare a Lucrezia. No, no, lui ha detto che tu sei la più brava, quindi
Egunon Gustioi.
questo è il, diciamo, il buongiorno di questo paese che ci sto affidando, di cui ci siamo tutti più o meno innamorati. E, come ho detto, i ringraziamenti li farò dopo. Allora, oh, no, aspetta.
Adesso?
Come vedete, insomma, questa cosa ha un titolo piuttosto impegnativo. Riflessioni sulla scienza, sull'integrità, sull'etica, sulla politica, sul coraggio, sulla libertà e sul sogno. Quindi voglio cominciare presentandomi. Io sono un uomo fortunato, incredibilmente fortunato. Ho indovinato le due scelte più importanti della mia vita, la compagna della vita e il lavoro. Sono innamorato di entrambi e lo sono sempre stato. E adesso che mi accingo a distaccarmi dalla mia professione, voglio riflettere senza veli, non per rinnegare qualcosa, come se mi fossi pentito, ma piuttosto per dare a chi mi seguirà, ai giovani che verranno dopo di me, un segnale che spero riesca ad essere da un lato di allarme, perché c'è bisogno di essere allarmati, ma dall'altro di fiducia e di speranza. La storia che vi voglio raccontare comincia ricordandovi cosa si intende per uno strano culto che ha avuto una vita relativamente breve ed è stato battezzato il culto del cargo. Se ne conoscono esempi già nel XIX secolo e testimonianze anche fotografiche nel XX. In particolare, durante la Seconda Guerra Mondiale, gli alleati cominciarono a partoriare ogni sorta di ben di Dio sulle isolette remote del Pacifico per motivi sostanzialmente militari. Vinta la guerra, il lancio cessò. In realtà i francesi poi presero a fare altri lanci, di questo parlerò più avanti. Fatto sta che le popolazioni indigene non potevano sapere cosa stesse succedendo ed immaginarono che lo stesso Dio che le aveva omaggiati per tanti mesi fosse in collera con loro e cominciarono a pensare di dover fare qualcosa. Costruire piste di atterraggio rudimentali o altri segnali che attirassero la benevolenza divina. Purtroppo nessuno di questi metodi funzionava.
e il nostro narratore, che qui è Richard Feynman, parte da questa storia per parlare di quello che spesso viene chiamata pseudoscienza. Vi presento dunque uno dei dei miti del giovane Enzo, uno scienziato, di cui ne nascono 2 o 3 magari al massimo per secolo, Richard Feynman. Questa è una foto molto triste, vedete, questa è una tribuna indigena, qua c'è una specie di aereo rudimentale, qua c'è una specie di rudimentale pista di atterraggio, un po' come i sacrifici che facevano nelle antiche tribù. Si sperava che questo propiziasse l'arrivo di nuovi aerei e l'argomento di Feynman parte da questo per dire che alcune pseudoscienze sono più o meno come questa. E dice Feynman, quello che voglio veicolare è una sorta di integrità scientifica, un principio del pensiero scientifico che corrisponde a una sorta di onestà assoluta. Per esempio, se state facendo un esperimento, dovreste riferire tutto ciò che pensate possa renderlo non valido, non solo ciò che pensate sia giusto. Altre cause che potrebbero spiegare i vostri risultati e cose che avete pensato di eliminare con qualche altro esperimento e come hanno funzionato per assicurarvi che gli altri possano capire che sono state eliminate. In sintesi, l'idea è di cercare di fornire tutte le informazioni che aiutano gli altri a giudicare il valore del vostro contributo, non solo le informazioni che portano a giudicare in una particolare direzione o in un'altra. Ed è questo tipo di integrità, questo tipo di attenzione a non ingannare se stessi che manca in gran parte della ricerca nella scienza del culto del cargo. Sempre Feynman che parla, il primo principio è che non dovete ingannare voi stessi e voi siete la persona più facile da ingannare. Vorrei aggiungere qualcosa che non è essenziale per la scienza, ma di cui sono convinto. Non bisogna ingannare i profani quando si parla come scienziati. Non sto cercando di dirvi cosa fare per tradire vostra moglie quando non state cercando di essere scienziato, ma siete solo un comune essere umano. Io sto parlando di un tipo specifico di integrità in più che non consiste soltanto nel non mentire, ma piuttosto nel farsi in quattro per dimostrare che forse si sta sbagliando, una cosa che si dovrebbe fare quando si agisce come scienziati. E questa è la nostra responsabilità come scienziati, certamente nei confronti degli altri scienziati, credo anche dei non addetti ai lavori. Poi è una persona incredibilmente intelligente, quindi finisce con un augurio particolarmente diciamo, attuale, perciò vi auguro di essere in un posto dove siate liberi di mantenere il tipo di integrità che ho descritto e dove non vi sentiate costretti dalla necessità di mantenere la vostra posizione nell'organizzazione o il sostegno finanziario e così via a perdere la vostra integrità, che possiate avere questa libertà. Questo è un discorso del 74 a Caltech, sono passati 51 anni. Anche io vorrei andare un po' oltre Feynman, cioè vorrei parlare di altre forme di tradimento dell'integrità della scienza. E la chiamerò la ricerca dell'integrità radicale. Feynman dice, quando si agisce come scienziati o scienziate bisogna essere radicalmente onesti. Dice, non sto cercando di dirvi cosa fare quando non state cercando di essere uno scienziato, ma siete solo un comune essere umano, vorrei dire un cittadino o una cittadina. Ora io pongo a me stesso e a chi mi ascolta una domanda circa la singola persona che studia scienza. L'integrità di Feynman è sufficiente a gestire il tremendo e formidabile potere della scienza? Si può tradire la scienza pur rimanendo fedeli alla lezione di Feynman? E la mia tesi è che purtroppo è proprio così che può andare e che in un certo senso è andata negli ultimi decenni. Si può tradire la scienza pur rimanendo fedeli alla lezione di Feynman. Serve un'integrità ancora diversa, quella che chiamerò l'integrità radicale. Come sapete, Feynman fu un attivo membro del progetto Manhattan, come tutta quella generazione ha dovuto fare i conti anche fisici, i tumori, eccetera, con il tremendo potere degli scienziati e delle scienziate. E forse ricorderete che il colonnello Paul Tibbets, che è stato il pilota di Enola Gay, pensava che la sua missione fosse stata necessaria per porre fine alla guerra e salvare vite umane. Cioè uno che sgancia una bomba che uccide sul colpo quasi 200.000 persone e segna per sempre la vita di altri centinaia di migliaia di persone, si dice convinto di aver salvato delle vite umane. Bene, allora io vorrei parlare dei frutti avvelenati della scienza. Come molti di voi sanno, è un momento in cui vivo con particolare sofferenza la dinamica universitaria. Credo che i frutti della scienza, almeno nell'ultimo secolo, so che farò dispiacere a molte persone presenti, ma lo voglio dire, siano per la maggior parte nocivi per il genere umano, per la vita sul pianeta. Se il pianeta Terra potesse parlare, credo che direbbe che l'università e la ricerca scientifica a livello planetario hanno fatto danni molto vicini ad essere irreparabili. Qualunque altro progresso non compensa questi danni. Cioè, bisogna guardare al bilancio, diciamo, tutte queste cose buone che sono state fatte, diciamo, quelle non buone che sono state fatte con l'uso della scienza, secondo me risultano di gran lunga e proverò a convincervi. Oggi esiste un contesto che è universitario, nazionale, internazionale, che è molto favorevole alla compressione delle libertà in tutto l'Occidente e la cosa va avanti, ormai programmata scientificamente da decenni. L'Italia in questo momento è il leader mondiale di suprematismo, neocolonialismo, bellicismo e la mia un tempo tanto amata facoltà è presieduta da una persona che con consenso maggioritario, questa è la cosa più importante, dichiara davanti a 400 persone di non voler prendere parola sull'uso delle nostre ricerche scientifiche. Testualmente disse: voglio che qualcun altro decida per me. E in questo modo certificando la genuflessione non sua personale, ma di una facoltà scientifica prestigiosa come quella della Sapienza al potere costituito. Come pietra di paragone, perché no, sembra che questo sia sempre stato così, il mite di Giorgi, cattolico, convinto, praticante assiduo, solo per citare un matematico celeberrimo, ficcava clandestinamente volantini antisovietici nelle valigie dei matematici che andavano in Russia, facendo rischiare la loro pelle. Chi diceva che se si rendesse conto che questi, se venivano beccati, stavano guai, rispondeva che sostenere la democrazia era più importante. Potrei andare avanti parlando dei fisici del calcolo di Amaldo, Calogero, protagonisti di motori, tutti i tentativi di disarmo nucleare, solo 50 anni fa, e sembra passata un'era. A mio parere ci sono ancora figure come loro a cui ispirarsi, ma non in queste discipline, in altre discipline del genere umano. Mi spaventa moltissimo l'idea ingenua di quasi tutti gli scienziati con cui parlo, che il problema risiederebbe nei leader mondiali. Quando uno dice questo, secondo me ha introiettato l'idea che conta solo quello che decide il capo, ma non è affatto così. Le nostre libertà fondamentali sono state minate, nel senso bellico del termine. Alcune sono state praticamente cancellate, altre traballano pericolosamente. La democrazia è ben più che in pericolo. Ne abbiamo perso quasi completamente le tracce, non esiste quasi più la stampa libera e proprio nei giorni scorsi la polizia americana ha sparato a una giornalista. Non sarebbe una notizia, l'ho fatta da decenni, ma questa volta non l'ha fatta in Palestina o in Sud America, l'ha fatta a Los Angeles. Per ora si tratta di un proiettile di gomma, ma la giornalista era in piedi, isolata, di spalle, ben visibile. Il proiettile era sparato da uno sniper, cioè da una persona addestrata, un militare, non un poliziotto qualunque. È un avvertimento, è anche un modo per educare e testare l'opinione pubblica. I giornalisti ci diranno sono pericolosi, abbiamo il diritto di difenderci e quindi anche. Il presidente americano è stato votato da 75 milioni di cittadini americani. Il genocidio a Gaza è sostenuto all'incirca dal 95% della popolazione dello Stato di Israele, con buona pace di chi dice il contrario. Cambiare il capo non risolve nulla. Se la situazione è questa, la scienza, in particolare le università, hanno una responsabilità enorme. Anzi, io temo che abbiano la responsabilità principale. La scienza è il nuovo feticcio che tutto può nascondere e manipolare. Facciamo qualche esempio. La BMW tarocca i valori delle emissioni dei gas. Che vuol dire? Che il potere economico corrompe degli scienziati, chimici, matematici, fisici, ingegneri, per far dichiarare i loro falso e fare l'esatto opposto di quello che chiedeva Feynman. Non è che questi scienziati non si rendono conto, si rendono conto benissimo. Le tragiche fatalità sul lavoro o altrove sono sempre legate a certificazioni false di scienziati compiacenti. Il controllo dei media, o dei media, come giustamente dice Luca, sulle informazioni sgradite è tecnologia avanzatissima. Il programma e il controllo degli abitanti di una striscia di terra o del globo intero, lo facesse inconsapevolmente, sarebbe uno scemo, e questo non è possibile. E allora è un feroce criminale, un dottor Mengele dei nostri giorni. Niente di più, niente di meno. Nessuna accondiscendenza o complicità deve essere tollerata, neanche il tengo famiglia. Non è una giustificazione sufficiente. Il progresso, perseguito dalla scienza, entrambe fra virgolette, di fatto ha lasciato un'impronta tragica di morte, distruzione, depauperamento delle risorse del pianeta da un punto di vista energetico, idrico, di biodiversità. Agli obesi occidentali, divenuta maggioranza negli Stati Uniti, fanno da contrattare miliardi di esseri umani affamati, assetati, privi di cure, vessati, sfruttati e in alcuni casi sterminati in nome di fantasie teocratiche. L'Europa segue l'America sempre più apertamente per gonfiare il PIL con massicci investimenti in armi di distruzione di massa. Nessuno si salva, né la fisica, né la chimica, né le cosiddette della scienza della vita, la vita di alcuni e la morte di altri, e nemmeno i purissimi matematici che sono parte decisiva insieme al mondo dell'informatica dell'assassinio scientificamente mirato di medici, paramedici, giornalisti, bambini, recentemente sperimentato su larga scala, parola d'onore di Dieppe. Come alcuni dicono di Mussolini, si potrebbe dire che anche la scienza ha fatto cose buone. A me pare che il punto sia che le scoperte scientifiche siano tutte, senza esclusione, uscite completamente fuori controllo e che la responsabilità principale sia degli scienziati e delle scienziate, non della politica, come spesso in maniera autoassolitoria ci diciamo. Se un genitore, tanto per giocare, mette un'arma in mano a un bambino che uccide il fratellino, la colpa non è del bambino. Nel mondo scientifico vige, secondo me, una diffusa e inquietante inconsapevolezza. Molti, troppi colleghi americani sono svegliati in patria solo adesso che la follia imperialista, colonialista, condita da intolleranza cristiana a sfondo religioso, li ha colpiti direttamente, tagliando i viaggi, gli stipendi, le conferenze. Ma l'ondata si stava ingrossando da decenni, 13 guerre con 40 trilioni di dollari utilizzati per uccidere con il pretesto delle false dichiarazioni dell'Occidente. Come è stato possibile non vederla? Come è stato possibile che decine di migliaia di ricercatori e ricercatrici di tutto il mondo non si sia reso conto di lavorare a un progetto diabolico? Dobbiamo, come scienziati e scienziati, a mio parere, fare autocritica urgente e durissima. Il pessimismo dell'intelligenza. Antonio Gramsci, citando Roland, premio Nobel per la letteratura, musicologo, fieramente antifascista, propugnava il motto pessimismo dell'intelligenza, ottimismo della volontà. La sua prossima frase sembra scritta adesso. Ogni collasso, adesso siamo vicino a un collasso, porta con sé disordine intellettuale e morale. Bisogna creare gente sobria, paziente, che non disperi dinanzi ai peggiori orrori e non si esorti a ogni sciocchezza. Pessimismo dell'intelligenza, ottimismo della volontà. A me, devo dire, fa difetto questa fede laica dei Roland e Gramsci, ma confido nella smisurata immaginazione dell'essere umano perché ne abbiamo avuto infinite prove, la prova della potenza di questa immaginazione. E quindi vi propongo di cominciare a immaginare l'imprevedibile. Quello che i popoli della Terra faranno per evitare che il mondo continui ad avvicinarsi alla scomparsa della specie umana, forse per fare posto a una specie meno aggressiva, meno gretta ed egoista, meno violenta, non sappiamo. Forse non faranno abbastanza, ma la Terra sopravviverà felicemente senza la razza umana. Se invece emergeranno delle idee per evitare la catastrofe, che razionalmente apparirebbe inevitabile, io credo che queste idee non verranno dalla cultura di coloro che hanno la grande parte della responsabilità, la cosiddetta cultura occidentale. L'Occidente oramai si identifica completamente con l'insieme degli stati che si oppongono al riconoscimento dello Stato di Palestina. Guardate la mappa per credere, gli stati grigi sono di colore e di fatto, America, Canada, Danimarca, Italia, Francia, Inghilterra, Australia e compagnia bella. Questi stati grigi comprendono l'America, che è nata dal genocidio dei nativi americani e prosperata sullo schiavismo, il Canada è meno noto da questo punto di vista, lo sterminio di almeno 50.000 bambini indigeni, i 150.000 che c'erano, cominciato nel 1863, continuato fino al 98. Cioè lì i bambini venivano internati nelle scuole che dipendevano dalla Santa Sede, quelli che parlavano la loro lingua, quella degli indigeni, venivano puniti cucendo la loro lingua sul palato. Nel 1998, non stiamo parlando del colonialismo del secolo scorso. Il Regno Unito, l'impero più spietato di tutti i tempi, probabilmente, come dice il grande economista esperto mondiale di geopolitica Jeffrey Sachs, quasi tutte le guerre attualmente in atto, provare per credere, sono eredità dell'ex impero britannico, a cominciare dalla ritirazione di Balfour. La Francia, ricordate De Gaulle, Algeri, le bombe atomiche in Polinesia? Io ho sentito con le mie orecchie un filmato in cui il capo del CNRS francese diceva che le radiazioni non erano nocive per la popolazione. Ora sono tutti malati, i polinesiani, cancri rari li chiamano, in sostanza danni da radiazione dopo decenni dai bombardamenti. La scienza non è complice, è protagonista di questo. E Macron dice che non si possono risarcire. L'Italia ha esportato il fascismo, con stupri di massa, torture, esecuzioni sommarie in Africa, e non se ne parla. Campi di concentramento in Italia, con tanto di ebrei denunciati da altri italiani per prendere loro le case, le terre, la dignità, anche di questo è sconveniente parlare. Molta gente non lo sa, pensa che i campi di concentramento ce ne fossero solo in Germania. Queste persone perseguitate da italiani, perché non dagli tedeschi, da italiani, perché ebree, le ho conosciute, sono parenti e ci ho parlato. Ancora l'Occidente, tutti quei paesi, sono tutti con passati colonialisti, il Portogallo, l'Olanda, la Danimarca, il Belgio, maestra dell'apartheid in Sudafrica, che è finita nel 94. con un evento inaspettato di questo parlare. I coloni australiani, sempre dall'Europa venivano, e sempre grazie all'impero britannico che ne ha fornito le basi teoriche di diritto internazionale, hanno quasi sterminato gli aborigeni. Per penultimo lasciamo la Germania, perché è l'unica nazione che ha riconosciuto di aver commesso 2 genocidi, la Namibia e l'Olocausto, e il cui premier odierno inneggia la pulizia etnica in Palestina senza tanti complimenti. Per ultima la Spagna, che accanto ad un passato non meno inglorioso di queste altre comunità sul piano coloniale, ha di recente riconosciuto la Palestina, rompendo insieme alla mitica Irlanda il fronte dei sudditi dell'impero. Al grido colonialisti di tutto il mondo, passati e presenti, corriamo tutti a soccorrere i nuovi colonisti, la Spagna e l'Irlanda hanno saputo resistere. A noi italiani, almeno a me personalmente, resta la vergogna di aver fatto il contrario. Dopo l'assalto a Capitolio feci la previsione che in America, in occasione delle successive elezioni, ci sarebbe potuta essere una guerra civile, fra le scompisciate risate di chi mi ascoltava. Oggi mi pare che ci sia più niente di ragionevole in quella previsione. I germi di guerra civile sono già in atto, gli americani si sparano l'un l'altro per le strade, anche se su scala ancora limitata, e non soltanto negli Stati Uniti. È sempre colpa di qualche pazzo, ma in realtà succede anche in Europa. Armi italiane, in dotazione al DF, hanno sparato agli italiani di UNIFIL. Questa tecnicamente è guerra civile. Italiani che sparano ad altri italiani, ma non si dice, non si può dire. Da questo Occidente che ho appena descritto e che ha smarrito ogni bussola morale per risolvere i problemi del mondo potrebbe solo venire un evento del tutto involontario, sia pure con probabilità esponenzialmente piccole, un incidente inaspettato, un suicidio politico basato sulla compiuta consapevolezza dell'importanabilità dell'impronta di morte e distruzione lasciata sul pianeta. Una persona mandata lì dalla classe dei super ricchi a dominarci per preservare il loro dominio, una persona che, come in un film poco plausibile, dica sorprendentemente basta, ci disarmiamo unilateralmente, giuriamo di non sparare nemmeno un mortaretto fuori dalle mura della nostra nazione. Sembra impossibile, eppure nessun politologo poteva prevedere che Gorbaciov si sarebbe unilateralmente disarmato. Per inciso, povero illuso fidato di inglesi e americani, perché si dice che non aveva studiato bene la storia. Oppure così imprevedibile come De Klerk. De Klerk fu eletto dai bianchi per continuare a reprimere i neri e decise di cedere il potere a Mandela, che fino al giorno prima era considerato un terrorista. Questa catarsi, pur essendo improbabile, non è del tutto irragionevole. Questi eventi non sono la politica come spesso ce la raccontano. Come dice lo storico Barbero, studiare la storia significa studiare gli uomini e le donne che l'hanno attraversata. Io credo che oggi più che mai la politica certifichi il trionfo della psicologia. Gli acclamati leader di oggi vivono di sogni, più precisamente di incubi. Sono fenomenali ad incarnare gli incubi di chi li elegge, esaltano gli incubi altrui. Eppure, come ho imparato leggendo un grande uomo del nostro tempo, Gabor Maté, nel suo libro Gabor Maté parla di un celeberrimo genetista che ha detto: l'essere umano è l'unico animale ad essere geneticamente programmato per non essere geneticamente programmabile. E dunque anche il più feroce carceriere potrebbe decidere di aprire tutte le porte e buttare le chiavi. E così sia. Adesso naturalmente ci deve essere una dimensione anche concreta in quello che uno fa, vive nella propria vita, e la mia, diciamo, personale ispirazione nel passato, e spero che in qualche modo possa esserlo per altri per il futuro, è usare la propria libertà per incoraggiare, ovvero per infondere coraggio. Quindi rimango in attesa che maturi questo istante in cui il Presidente degli Stati Uniti decide che il Consiglio di sicurezza dell'ONU debbano formare le 7 nazioni più popolose al mondo, che il diritto di veto lo possa esercitare solo l'Assemblea solo nel caso le nazioni superano tutti insieme il 50% della popolazione mondiale. Tutte cose molto sensate se crediamo nella democrazia, purtroppo sono cose che fanno inorridire i colonialisti del nostro mondo. In questa presumibilmente lunga attesa vi propongo un frammento del mio eterno piccolo sogno: cambiare il mondo. Noi, quelli che fra noi hanno il privilegio di insegnare, quelli che fra noi appartengono a circa l'8 per 1000 più ricco di conoscenze al mondo, noi abbiamo uno spazio particolarmente prezioso per alimentare la speranza, uno spazio che almeno noi italiani siamo tenuti a preservare. La Costituzione dice questa bellissima cosa: ogni cittadino ha il dovere di svolgere, secondo le proprie possibilità e la propria scelta, un'attività, una funzione che concorre al progresso materiale o spirituale della società. Ha il dovere, non sta parlando del lavoro, sta parlando di qualche altra cosa. Chi ha i privilegi che ho io chi come me ha beneficiato di investimenti incredibili dello Stato, istruzione, sanità, sistema pensionistico e via dicendo, chi come me ha raggiunto quell'1% più ricco culturalmente del pianeta, quelli come me hanno doveri e responsabilità diversi da chi non ha avuto reale accesso alla conoscenza, alla sanità pubblica o al lavoro. Molti tra noi sono persone che a volte non pienamente consapevoli hanno un'enorme libertà. Se disposti a fare delle rinunce, come Emanuele e Luca per esempio, e tante altre persone qui presenti, possono utilizzare questa libertà. Bisogna rinunciare alle facili lusinghe di essere apprezzati dai capi o dalle cape. Penso a tutti quelli che insegnano, che non sono affatto solo gli insegnanti di professione, ma adesso parlo degli insegnanti professionisti, poi passerò con gli altri. Che fare in classe? Limitarci ad insegnare quanta più tecnica matematica o geologica o fisica sia possibile? O dobbiamo invece valutare attentamente il rischio di scollegare la tecnica dall'etica? Il rischio di formare persone che spensieratamente, in quanto radicalmente e colpevolmente inconsapevoli, aiuteranno gli eserciti più potenti del mondo a devastare in maniera accurata, secondo il celebrato metodo scientifico. Scientifico e disumano non sono affatto in contraddizione. La scienza, disancorata dall'etica, è inevitabilmente destinata ad essere permanentemente diabolica. La sintesi di quel che ho detto potrebbe essere questo: la salvaguardia della scienza, intesa come un valore nobile, come tutti noi che abbiamo studiato scienza ci hanno sempre un po' inculcato, non risiede affatto nel metodo scientifico. Questo non è affatto vero. Molti scienziati purtroppo pensano al metodo scientifico come un riferimento etico, e a mio avviso questa è la chiave: fedeltà all'integrità scientifica, ma tradimento dell'integrità radicale. La salvaguardia della scienza, intesa come un valore nobile, a mio avviso, risiede nel riconoscimento dello Stato di diritto in patria, del diritto internazionale nel mondo, nella consapevolezza della complessità dei contesti socio-economici, nel riconoscimento incondizionato della sacralità della vita di tutti gli esseri viventi. E pertanto la formazione di scienziati radicalmente integri deve contenere questi elementi, altrimenti non c'è speranza. Non è insegnando più matematica e più fisica che avremo scienziati più integri. Credo sia nostro preciso dovere praticare e instillare un tipo di integrità radicalmente più profonda di quella che evocava Feynman. Questa integrità si nutre della libertà. E qui cito la mia amica Alessandra Cerant, che mi mandò, a proposito delle mie battaglie contro una persona veramente malvagia, una frase di Tucidide: il segreto della felicità è la libertà, e il segreto della libertà è il coraggio. Mi voglio dedicare alle persone, alcune presenti da remoto, che lavorano nello Stato in ruoli diversi dal mio, una frase che scrissi tanto tempo fa e penso sia ancora attuale: le persone che lavorano per dare maggiori opportunità di accesso allo studio, che lavorano per contrapporre a quella che io chiamo la logica del respingimento alle frontiere della conoscenza, la logica invece dell'accoglienza culturale, umana e psicologica, sono spesso poco riconosciute, e invece meritano una grande riconoscenza. La mancata immissione nei livelli influenti della società di persone che hanno provato le difficoltà dell'emarginazione, oltre ad essere eticamente riprovevole, ammala la società, che si infetta di un crescente disprezzo per i deboli, e quando vede i segnali di una possibile ribellione dei diseredati risponde con la forza bruta della repressione. L'immaginazione come atto di coraggio, ma anche di realismo, la potenza del sogno. Il sogno che vorrei condividere con voi è l'ascolto di una legge morale, un richiamo dell'essere umano che non cessa ed anzi si esalta di fronte alle difficoltà. Abbiamo il dovere morale, noi ricchissimi di conoscenza, di condividerli con i poverissimi di conoscenza, quanti più poverissimi sia possibile. E oggi un parallelo evidente: c'è chi sostiene che essere poveri è una colpa. Questo principio è stato condito da slogan di vario tipo per deridere e denigrare i giovani, fannulloni, chiusi, apatici. In questo modo si crea il terreno ideale per i ricchissimi, continuano ad accumulare ricchezza a danno dei poveri e sostengono contro ogni evidenza che questo faccia bene all'economia, alla borsa, all'Europa, all'Occidente, a Dio in carne e ossa. Un perfetto parallelo con chi sostiene che essere privi di conoscenza è una colpa individuale, e come tale debba essere colpita con l'ulteriore esclusione dalla conoscenza. Questi ricchissimi, che siamo proprio noi, continuano a studiare metodi per escludere i poveri dalla conoscenza. Test ingresso, precorsi, questo e quell'altro. La conoscenza si vende o si regala solo per merito, ovvero il censo economico e sociale. Questo approccio è immorale, danneggia l'umanità intera e fa venire voglia della ferocia della rivoluzione culturale di Mao. La legge morale, o se volete la Dichiarazione dei diritti universali del genere umano e la Costituzione italiana ci impongono di rifiutare questo modello della mattanza intellettuale dei diseredati. Continuare con coerenza a professare queste idee oggi sembra particolarmente difficile, ci vuole coraggio appunto, il coraggio della coerenza. Permettete qui un piccolo riferimento personale, quanto mi sia costato cercare nel mio piccolo questo ideale, non so più quantificate, a parlare chiaro a persone molto più potenti, decisamente più aggressive di me, centinaia, forse migliaia di volte. Rivendico però una consapevolezza, al meglio delle mie possibilità, ho cercato di avere il coraggio di dire le cose come le vedo. Anche oggi sicuramente dirò cose che non piacciono a tutti, ma non è importante perché forse anche cose sbagliate, ma io rivendico l'importanza dell'errore. Quando si parla di cose che si conoscono, quando non si sbaglia, non si impara nulla, e quando si sbaglia che si impara qualcosa. In questa coerenza rivendico specialmente la tenace ricerca della giustizia nei confronti di coloro a cui abbiamo il privilegio di insegnare, una ricerca che non si può esaurire soltanto della capacità brillantissima di spiegare un concetto in maniera deliziosamente semplice e elegante, quella è la tecnica. Bisogna invece conoscere chi vorrebbe essere in classe ma non riesce a esserci, chi vorrebbe studiare ma non può, e bisogna lottare con tutta la nostra forza intellettuale perché possa fruire della nostra conoscenza, bisogna essere dalla parte dei deboli, delle oppresse, di chi non ha voce, anche quando sembra che siamo tremendamente isolati, un compito non derogabile. Vorrei sottolineare che l'insegnamento non è legato alla specifica professione, tutti possiamo e dobbiamo insegnare e parlerò di questo nei ringraziamenti e nelle conclusioni. Quindi comincio dai ringraziamenti. Se oggi siamo qui si deve a un riconoscimento. Penso che l'idea in originale non mi è stato mai confessato sia di Luca, ed è, diciamo, nemo profeta e padre, come si dice. E ho accettato questo affettuosissimo regalo con un misto di sorpresa. La prima reazione è stata sorpresa, la seconda è stata paura, la terza è stata pudore e poi finalmente gioia. Ci ho messo, diciamo, non so, 12 ore per scrivere, per ringraziare chi me l'aveva proposto. Grazie anche di cuore a chi oggi sta qui da remoto. Starmi accanto ultimamente è diventato uno sport pericoloso, quasi estremo, molti sono fuggiti, non li biasimo, ma è la realtà. Qui mancano alcuni protagonisti della mia vita e quindi non ne parlerò perché non sono qui. Invece ho qui parte del mio quadrato. Nathan purtroppo deve occuparsi del matrimonio del fratello, comunque Marco, Maria Pia e Nathan sono persone con le quali ho lavorato negli ultimi anni, mesi. Voglio ringraziare te, Maria Pia, per avermi insegnato a riconoscere tanti miei difetti, ma soprattutto per essere stata la mia guida intellettuale e spirituale nel terribile viaggio virtuale in Palestina. Per cercare di starti al passo, sia pure senza riuscirci, ho aumentato di ordini di grandezza la mia consapevolezza sull'argomento. Marco e Nathan invece desidero ringraziarvi perché voi mi avete sempre voluto bene e in più chi ha la maniera finnica e chi ha la maniera hawaiana me lo avete sempre dimostrato apertamente. Anche se presente almeno in parte da remoto, c'è anche un triangolo. In matematica non so perché però i triangoli sono ABC o CDE, questo CDE è questo triangolo. Carlo Ioni e Davide Zaccagnino sono stati persone che hanno veramente riempito la mia vita scientifica e non negli ultimi anni. Carlo è uno scienziato, è un amico straordinario e Davide, che è allievo di Carlo, per me è un elemento di speranza. Non perché sia un giovane bravo, perché ce ne sono tanti, a mio parere fenomenale, ma non è questo il punto. Il punto è che il suo temperamento, non solo i suoi interessi scientifici, lo hanno portato a scegliere Carlo, che è un grande esempio di integrità. Gli dobbiamo tutti molto in Italia, anche se in pochi lo sanno, forse neanche lui se ne rende conto. E sono certo che Davide seguirà Carlo anche sulla strada dell'integrità radicale di cui ho parlato prima. In cuor mio spero che anche io sia stato scelto come mentore pro tempore da Marco, Maravia e Nathan per la stessa ragione. Poi qui ho presente al completo il mio Dream Thinkers del nuovo, diciamo, l'icona è un po' suggestiva per noi che abbiamo studiato questo problema in questi ultimi tempi. Queste persone, Emanuele, Eugenio, Flavia, hanno costituito qualcosa che per me significa la differenza fra non sapere per quale motivo dover andare in dipartimento, che così sarebbe se non ci fosse il team, e la felicità con cui mi sveglio la mattina quando penso che ci incontreremo per il nostro rito, fare matematica con serietà, ponendoci domande alle quali non sappiamo rispondere. Suona strano, ma credo che molti si facciano solo domande di cui già si conosce la risposta, e facciamo questo in calviniana leggerezza. So in cuor mio quando l'incontro che passare del tempo insieme è già un premio. Se risveliamo dei teoremi alla nostra ignoranza, ne siamo contenti. Se rimangono avvolti del mistero, il premio consiste nell'immaginarne altri. Per me la vostra presenza è un grande regalo, no? Flavia è stato un sostegno continuo e particolarmente prezioso quando abbiamo insegnato insieme. Eugenio se la batte con Giovanni Alessandrini, è una persona incredibilmente buona, capace e generosa. Con Emanuele è un po' speciale per me, forse è una questione di paralleli, cioè siamo vicini, latitudini. Bellissima sensazione di sentirsi sempre compreso, anche quando sbaglio, a causa degli innumerevoli difetti citati da Luca e di cui il mondo intero potrebbe fornire documentata. Una menzione speciale va al nostro ospite, Luca Fanelli. Luca ci manca ogni giorno da quando è venuto qui. Non voglio parlare di perdite, e quindi dirò che quello in cui Luca e la sua famiglia hanno lasciato Roma è stato un grande giorno per i Paesi Baschi, per la matematica dei Paesi Baschi, per la musica dei Paesi Baschi, per il senso dell'umorismo dei Paesi Baschi e per rimanere in tema, per l'integrità dei Paesi Baschi. Evidentemente nel mio dipartimento operano delle generose personalità che pur volendo rimanere anonimi hanno lavorato indefessamente per la donazione di questa talentuosa famiglia ai nostri fratelli e sorelle basche. E siamo alle conclusioni. Voglio finire tornando all'insegnamento, un'attività straordinariamente nobile e connaturata all'essere umano e direi a molte, qua ci sono delle biologhe che mi ascoltano, spero di non dire scemenze, se non tutte le forme di vita. I primi insegnanti, per chi li ha, sono i genitori, che si sia umani, primati, orche, leoni o leonesse. Quelli sono i primi insegnanti. E tutte le persone che ho citato e quelle che citerò oggi hanno in comune una cosa, sono stati grandi insegnanti per me. Qui mi rivolgo a tutte le persone che in questo momento sono in ascolto e che magari ascolteranno in un altro momento questo mio saluto. C'è una lunga lista di persone che sono a seguirmi da lontano. Per questo mio saluto che un arrivederci consapevole del difficile momento. Io non credo che negare la realtà sia mai qualcosa che porta da nessuna parte, un momento storico per la comunità romana, ma traboccante di gioia individuale per me, per Enzo. Il mio augurio, per chi ha la fortuna di insegnare qualunque cosa e a chiunque, che sia ai bambini di pochi mesi o anni e nella veste di genitori, nonni, zii, maestri, così ad adulti maturi, e che insegnando si semini il gusto della libertà, si coltivi il valore dell'integrità e che molte donne e molti uomini in futuro si ricordino di voi come quei professori, professoresse, maestre, mamme, padri, nonne, nonni, zii, zie che hanno cambiato la loro vita, rendendola migliore in quanto più libera. Che per questo vi possiate meritare la loro imperitura riconoscenza. E vi auguro che il destino di quelle specifiche persone per le quali avete seminato e di tutti quelli che con loro avranno a che fare sia cambiato per sempre anche per merito vostro. Se si insegna, non si sbaglia mai se si incoraggia e si sbaglia sempre se si rimprovera prematuramente. Diceva il mio grande amico Luca Serianni, chi insegna non può permettersi il lusso del pessimismo. Il mio augurio per me è di conservare l'amicizia sincera e generosa che mi avete mostrato in 1000 occasioni e di conservarla non soltanto per partigianeria, perché mi avete voluto bene e continuate a farlo per inerzia. No, mi auguro di poter avere di più di una semplice isteresi degli affetti, che io sia capace di continuare a meritare il vostro affetto anche per come sarò nel futuro. Più di ogni cosa sogno che io possa continuare a meritare i lavori di Maria Grazia, dei miei figli, Mimmo, Leandro e Giovanni, anche loro in ordine di apparizione, delle mie figlie, Raffaella, Deborah e Lavinia, dei miei nipoti, Ludovica, Damiano e anche di quelli che ancora non sono stati immaginati. E qui chiedo a Lucrezia di nuovo di chiudere tu col saluto perché qua mi potrei veramente confondere.
Stavo cercando la traduzione in realtà. Emanta Saval Sasu Yaginsa.
Questa è una citazione che è il motto dell'università, è un motto generoso di donazione e penso che sia molto appropriato per salutarvi. Vi voglio guardare la telecamera per ringraziare tutti quelli che sono collegati, sono molto contento, sono molto commosso del fatto che ci siate voluti.